How to compute runoff coefficients. Here we have an existing stormwater project with a set of subbasins that make up the drainage area. The subbasins have already been delineated, and now we need to assign runoff coefficients to each subbasin so we can move forward with the hydrologic analysis. If you haven't gone through subbasin delineation yet, that's covered in a separate tutorial. The link is in the corner of the screen and in the video description below. In this tutorial, we're going to focus on the ComputeRC command, how to open it, how to configure it, and the different ways to bring land use and soil data into the calculation. But before we dive into the software, let's take a moment to talk about what a runoff coefficient actually is and how it works. What is a runoff coefficient? A runoff coefficient, often denoted by C, is a dimensionless value between 0 and 1 that represents the fraction of rainfall that becomes surface runoff. A value of 0.20, for example, means only 20% of the rainfall becomes surface runoff, with most of it infiltrated into the ground before it reaches a channel. The value of the runoff coefficient depends on several factors: the land cover, the underlying soil type, and the slope of the terrain. Higher intensity or longer duration rainfall events can also push effective runoff higher as the rate of rainfall exceeds the ground's infiltration capacity. A densely developed area with high impervious cover, such as pavements, rooftops, and parking lots, will have a high runoff coefficient, often 0.70 or higher, because water cannot penetrate these impervious surfaces and nearly all of the rainfall becomes surface runoff. A wooded area or open field with well-drained soils, on the other hand, might have a C value as low as 0.10 or 0.15 because much of the rainfall infiltrates into the ground, contributing very little to surface runoff. In practice, most drainage areas contain a mix of different land cover types and soil conditions. The ComputeRC command handles that by computing a composite runoff coefficient for each subbasin, a weighted average of the C values for each land use and soil type combination within the subbasin. The subbasin's average slope also factors into the calculation, since steeper terrain tends to generate faster and more concentrated runoff. Now that we have a solid picture of what the runoff coefficient represents, let's talk about why you actually need to compute it. The runoff coefficient is a core input for the rational method, modified rational method, and DeKalb Rational method, and it's worth taking a moment to understand exactly why it matters so much. At its core, the formula expresses peak flow as the product of three values: C, the runoff coefficient; I, the design rainfall intensity; and A, the drainage area. Together, they give you Q, the peak flow rate for that subbasin. It's worth noting that the formula looks slightly different depending on the unit system in use. The formula shown on screen works for U.S. customary units, where intensity is in inches per hour and drainage area is in acres. In SI metric units, a unit conversion factor K needs to be applied to this formula, where intensity is in millimeters per hour, drainage area is in hectares, and the resulting flow is in cubic meters per second. In practice, Ka works out to approximately 0.00278. You can enable this conversion by checking the corresponding option under General Preferences in the Options Backstage page. Because C appears as a direct multiplier, even a small difference in its value will shift your computed peak flows proportionally. Underestimate it, and your pipes, inlets, and channels may be undersized. Overestimate it, and your design ends up more conservative than necessary. Either way, the analysis is only as reliable as the C values you assign, and without them, the software cannot run the computation at all. Using the ComputeRC command, we are going to head over to the Watershed ribbon menu. This ribbon menu contains many drainage-related commands, including the Compute Runoff Coefficient, or ComputeRC command. Clicking on this command opens the Compute RC dialog box. The first thing you'll see in the dialog is the Select Subbasins section. This lists all the subbasins in your model, along with two key columns. The average slope column shows the terrain slope for each subbasin expressed as a percentage. These values are computed using the Compute Slopes command, which processes your project's terrain data to compute the average slope across each subbasin. If you haven't run that step yet, we walk through it in a dedicated tutorial. The link is in the video description below. The computed RC column is empty for now and will populate once the computation runs. Check the top checkbox to select all subbasins at once, or check individual subbasins if you only need to update specific ones. You can select the subbasin directly from this table or click the Pick button. This will temporarily hide the dialog and allow you to select subbasins interactively from the map view. After you've made your selection, right-click and choose Done from the displayed context menu to return to the dialog. Now that we have our subbasins selected, let's move on to the Define Computational Data section, where we tell the software what land use and soil information to use for the computation. Defining computational data. To compute a composite runoff coefficient, the software needs two pieces of information: what's covering the ground surface and what type of soil is underneath it. The Define Computational Data section lets you configure both, and for each one, you have a few different options depending on what data you have available. This section is organized into three panels: land use data, hydrologic soil type data, and intermediate results. This section works the same way as the Define Computational Data section in the Compute Curve Numbers tutorial. If you haven't seen that one yet, the link is in the video description. The one difference is in the lookup table under the Land Use Data panel, which maps each land use and soil type combination to a runoff coefficient value rather than a curve number. The hydrologic soil type data and intermediate results panels work exactly the same way in both. Now let's go through each panel briefly. Land use data. The land use data panel gives you three ways to bring land cover information into the calculation: the NLCD online layer, your own GIS Polygon data, or a default value. Let's walk through each option. The first sub-panel is the NLCD layer. For projects in the United States, this uses the Online National Land Cover Database, or NLCD, to classify land types across your project area. For projects outside the United States, the software can access other available online land cover databases for many countries around the world. The content of this sub-panel will automatically update based on the database available for your specific project location. Once you select your data source and run the computation, the software cross-references each subbasin's land cover types against the RC lookup table to assign the appropriate runoff coefficient for each combination. You can also click the Edit button to view or adjust the default RC values in the table if your project conditions require it. The GIS Polygon layer option is for projects where you have your own land use polygon data. Once you select your layer, the software can work with it in two ways, depending on how the data is structured. Polygons that already carry a direct runoff coefficient value are mapped using the runoff coefficient attribute field, and the software reads those values directly. For polygons classified by land use type, the standardized land use type attribute field tells the software to cross-reference those types against the RC lookup table and assign the corresponding values. The third option is default values. This option lets you assign a single runoff coefficient across all selected subbasins by defining a default value in the RC value field. You can also leverage the standardized land use RC values for the software to cross-reference. This option is a useful shortcut for early-stage estimates. That covers the land use data panel and its three subpanels. Now let's move on to the remaining two, hydrologic soil type data and intermediate results. Both work exactly the same way as they do for computing curved numbers. Hydrologic soil type data. The hydrologic soil type data panel is where you define the soil data for the computation. You have three options here as well: the NRCS online soil survey layer for the USA, your own GIS soil Polygon data, or a single default hydrologic soil group. Let's start with the first subpanel, NRCS layer. For projects in the United States, this subpanel pulls soil data from the online NRCS soil survey database to determine the hydrologic soil group across your watershed. This is usually the most common and efficient approach for US-based projects because the data is already available and can be applied directly to your model. For projects outside the United States, the software can provide access to similar online soil survey databases from other countries and regions. Just like with the land cover panel, the available options will automatically update based on your project location and the soil data available for that area. The second subpanel is the GIS Polygon layer. This is used when you already have your own soil map data. For example, you may have soil polygons from a local agency, a regional database, or a data set that your team has already processed for the project. In that case, you can use your own GIS soil layer instead of relying on an online soil database. The third subpanel is default value. This option lets you manually assign a single hydrologic soil group across all selected subbasins. This can be useful for simplified analyses, early planning studies, or situations where you do not yet have detailed soil data available. Select the option that matches the data available for your project area, and the software will combine it with your land cover data to compute the composite runoff coefficient for each subbasin. Intermediate results. The intermediate results panel lets you save the spatial output from the computation as a shapefile. When this option is enabled, the software creates separate GIS polygons for each unique land use and soil group combination across the selected subbasins. So instead of only seeing the final composite runoff coefficient for a subbasin, you can look behind the scenes and see exactly what went into that calculation. You can see which land use types were used, which soil groups they were paired with, where those areas are located, and how much area each combination represents. This is helpful for checking your work, documenting your assumptions, and creating engineering exhibits. To turn this on, check the Compute Intermediate Results checkbox. You can also choose whether the results should be automatically loaded into the project after the computation is complete. Then, use the Browse button to select where the intermediate results should be saved. Now that the land use data, soil data, and intermediate result options are set up, we are ready to compute the runoff coefficients. Computing and reviewing runoff coefficients. With the subbasins selected and the land use and soil data configured, click the Compute button. The software reads the land cover and soil data for each selected subbasin, applies the corresponding values from the lookup table, factors in the subbasin's average slope, and computes a composite runoff coefficient for each one. When the computation finishes, you'll see the computed RC values in the Compute RC dialog for each subbasin. These values are editable directly. If you need to override a result based on engineering judgment or local conditions, you can do that here before closing. When you're done reviewing the results, click Close to return to the main project view. It's worth noting that the computed values are also stored in the subbasin data dialog, so you can review them there as well at any point later in your workflow. And that's the complete workflow for computing runoff coefficients using the Compute RC command. Whether you're pulling land cover and soil data from the online NLCD and NRCS sources, using your own GIS polygon layers for a more site-specific result, or assigning a default value for a quick preliminary estimate, the command handles all of those cases and assigns the results directly to your subbasins. Once the runoff coefficients are in place, you're ready to run your analysis and compute peak flow rates for your drainage area.